Now we have a large object falling through the air. What type of drag force would we have for a large object? Correct! Isabel, good answer. It's going to be inertial drag. So a large object of mass m starts at rest and falls through the air on a day with no wind. Determine the position, velocity, and acceleration as functions of time. Here's our free body diagram. The dot represents the object, force of gravity downwards, Fg, drag force upwards, Fd, acceleration is down, and let's take the x-axis to be positive going down, and we'll start at x equals 0 when t equals 0. Let's find the differential equation. So first of all, the net force from this free body diagram, Fg minus Fd, and that equals ma. Fg is just mg, Fd is kv squared. This is inertial drag, so it is proportional to v squared. And a is dv by dt. Let's put these three things into our equation from Newton's second law, and this is what we get. This is our differential equation. mg minus kv squared equals m dv by dt. Note the difference between the case for viscous drag. For viscous drag, it was just v. Now for inertial drag, it is v squared. This becomes a harder problem to solve because we have v squared instead of v. How can we solve this problem? Of course, we need to use separation of variables. So here's our equation. So let's divide by mg minus kv squared, multiply by dt, and we get this. Now we have v's on the left side and t's on the right side, so we can integrate. Here's what we get, taking the m out of the integral since m is constant. Now, before, when we had viscous drag, this was just a v here, not v squared. And then we could use a u-substitution. And it was going to be ln u was the answer. But now it's more complicated to solve this integral. So let's rewrite it like this. Let's divide by the left side. Let's divide the numerator and denominator on the left side by k, like this. So m divided by k, mg divided by k, and k divided by k. So we get this, m over k times this. And now, let's say that this factor here is a squared. So a squared is mg over k, and therefore a is square root mg over k. This integral on the right is very easy to solve. It's just t. This one on the left, we can use, one way is to use trigonometric substitution. I can write it like this, by the way. I multiply by negative k over m, so I get negative k over m here. Here I have v squared over a. Up here was a squared minus v squared. But I multiply by negative 1, so now it's v squared minus a squared. So as I said, we could use trigonometric substitution to solve this problem, this integral. Or we could use the method of partial fractions. Both ways work. Today I will show the method of partial fractions since I think it's more straightforward. So we can write this. 1 over v squared minus a squared equals b over v minus a plus d over v plus a. B and d are constants which we need to find. On the right side, let's get a common denominator, which is v minus a times v plus a. So we get b times v plus a plus d times v minus a for the numerator. V minus a times v plus a is just v squared minus a squared. So the numerators of this and this must be equal to each other. So we have this. b times v plus a plus d times v minus a equals 1. We have to solve this equation for the constants b and d. There's two methods to do this. Let's look at method 1. Let's find all the terms that contain v in them. So on the left side, we have BV plus DV. And on the right side, there's no V, so it's 0V. So we get this equation, V plus D equals 0. Now let's look at all the constant terms. On the left side, we have BA plus D times negative A. And on the right side, we have 1. So we get BA minus DA equals 1. So we need to solve these two equations for B and D as functions of A. From the first equation, you get B equals negative D. So put this into here. And we get negative dA minus dA equals 1, or D is negative 1 over 2A. And since V equals negative D, we get V equals 1 over 2A. So now we've got the two constants. Let's look at method 2. This equation is true for all values of V. It is true for V equals A. So let's put V equals A into this equation. Here we get V times A plus A plus D times A minus A. This is just 0. That's why I chose V equals A. So we get B times 2A from here plus 0 equals 1. So B2A equals 1. Therefore, B is 1 over 2A. Now let's put B equals negative A. First term here is going to be 0. Negative A plus A is 0. That's why I chose V equals negative A. Second term is D times negative A minus A equals 1. So D times negative 2A equals 1. D equals negative 1 over 2A. So now our integral becomes this. And this is easy to solve. This is ln V minus A. This is ln V plus A. So here's what we get for our integral equation. And let's multiply by 2a and then solve the integral. So we get here ln V minus A minus ln V plus A minus 2a k over m times t plus c1, where c1 is a constant. Note, when we do the ln function, we're taking absolute values. That will become important later. Let's simplify some more. ln V minus A over V plus A equals negative 2 square root kg over mt plus c1. And we want to get rid of the ln, so we take e to the ln, and e to the negative 2 times this. This exponential function on the right can be written as two factors, e to the c1 and e to the negative 2 square root kg over m times t. And this, when we take e to the ln, we just get v minus a over v plus a, and so it equals c2 times e to the negative 2 square root kg over m times t. Now we have to take care of this absolute value function. To do that, we need to consider the terminal velocity. When we have a large object falling through the air, the terminal velocity is the maximum velocity. So when v equals vt, the net force is going to be 0. So Fd equals Fg. Fd is kv squared for a large object. It's inertial drag. And when v is vt, Fd is kvt squared. So kvt squared equals mg. Solve for vt. Vt is square root mg over k. We just saw this. Square root mg over k. Square root mg over k is the a in our equation. So the velocity is always less than or equal to vt. So velocity is always less than or equal to a. So therefore, when we do this absolute value, v minus a is going to be negative or 0. So when we take the absolute value, we need to reverse it. It becomes a minus v, because a minus v is positive. So we get a minus v over v plus a equals c2 times the exponential function. Here's what we have. Now we need to determine the constant c2. So we need a condition. What is our initial condition for velocity? At t equals 0, v equals 0. So let's put these two things into this equation here. This is what we get. A minus 0 over 0 plus a equals c2 times e to negative 2 square root kg over m times 0. This is just a over a, which is 1. This is e to the 0, which is 1. So we get c1 equals c2. So we'll put 1 into our expression there for c2, and we get this. A minus v over v plus a equals e to the negative 2 square root kg over m times t. Here's what we have. Now let's solve for v. Multiply by v plus a, like this. Then find all the terms that contain v and put them on one side of the equation. And all the terms that do not contain v, put them on the other side of the equation, and we get this. So now divide by this factor, and we get this. So this is our velocity. Square root mg over k. This is the terminal velocity. Times 1 minus e to negative 2 square root kg over mt over 1 plus e to negative 2 square root kg over mt. Let's check this solution. When t equals 0, these exponential functions become e to the 0, which is just 1. So this is a 1 and this is 1. So we get 1 minus 1 over 1 plus 1, which is just 0. So when t equals 0, v equals 0, as expected. When t goes to infinity, now these exponential functions become e to the negative infinity, which is just 0. So what's in parenthesis becomes 1 over 1, which is 1. So v equals square root mg over k. It equals the terminal velocity is a constant. That is what we expected. This looks like a good solution. Now we need to calculate the acceleration. This is v. Acceleration is dv by dt. Here we have a quotient, a function in the numerator and a function in the denominator. We could use the quotient rule. d by dt of f over g equals f prime g minus fg prime over g squared. So let's apply the quotient rule to this function. First of all, we got the constant coming out in front, square root mg over k. Square root mg over k. Then here we squared the g. So this is the g, and we squared it and put it here. Now, here, this is df by dt. So derivative of this, derivative of 1 is 0, and derivative of this, we have the negative, and then we got negative 2 square root kg over m coming in front when we take the derivative of the exponential function. So that's f prime. And then this is g, right here. They're the same. Then minus f, so this f is over here. Then we got here, this is g prime. The derivative of 1 is 0. Derivative of the exponential is this. We get the factor negative 2 square root kg over m coming in front. So that is what we get by applying the quotient rule. Now let's simplify further. This factor, 2 square root kg over m times square root mg over k, is 2g. And then some things cancel out. Let's look at what cancels out. Negative times a negative times a positive. That's a positive. Negative times a negative times a negative is a negative. So this cancels out with this. And then we are left with the ones. And this first one is going to be a positive, because negative times negative is positive. Second one is also positive, because we have negative times a negative. And so we get a factor of 2. 1 plus 1 is 2. And so we get a 2 times e to the negative 2 square root kg over m times t. And then bring the 2 out in front, and finally this is what we get. A equals 4g times e to the negative 2 square root kg over m times t over 1 plus e to the negative 2 square root kg over m times t squared. Let's check this solution. When t equals 0, the exponential functions are equal to 1. So we get 1 over 1 plus 1 squared. So 4g times 1 over 1 plus 1 squared. 1 plus 1 squared is 4, so we get g. That's what we expect. When t equals 0, a equals g. At t equals 0, the drag force is 0 because velocity is 0. So we only have force of gravity acting. So a equals g. Now when t goes to infinity, these exponential functions become e to the negative infinity, which is 0. So we have 0 over 1 plus 0 squared, which is 0. So a equals 0. As expected, after a long time, the velocity is constant. The velocity is the terminal velocity, so unchanging velocity means acceleration is 0. This solution makes sense. Now let's calculate the position. So here's our expression for velocity. And that equals dx by dt. So this is our differential equation. Let's separate variables and then integrate. So I multiply by dt and then integrate it. So we have this integral on the left, which is very easy. It's just x. And then we have this more complicated integral on the right. Let's look at that complicated integral. Let's consider it to be two separate integrals from each of these two terms in the numerator. So we have this integral and this integral. This integral can be easily done. We can do a u-substitution. If u equals this in the denominator, then du is proportional to this in the numerator. So a u-substitution will work. We would have integral of du over u, which is ln u. This one, we need to put it into this form. To do that, we multiply by e to the 2 square root kg over m times t. This is what we get. So we multiply through by this. So this is what we get in the numerator. Denominator becomes this. E to the 2 square root kg over m times t plus 1. So this now is in a form where we could do a u-substitution. If u equals what's in the denominator, then du would be proportional to what's in the numerator. And this would again be integral of du over u, which is ln u. So now these integrals can be solved. So here's, I've written now in terms of the two things, this one and this one. Let's do this u-substitution for the one in blue. That's u, this is du. For the red one, let's do w. This is w, this is dw. Put these into the integrals and we get this. We have an integral of dw over w, integral of du over u. Well, this is just ln w. This one is ln u plus a constant c3. And then we could combine these two ln functions, gives us ln wu. Okay, so this is what we got for this integral. And w is this, u is this. Let's multiply them together. When we multiply w times u, we get this. And so now, this is let's go back to our integral equation. This is what it was. Now what do we have? We just found that this integral here is equal to this whole thing here. So let's put that into there. And integral of dx is just x. So this is what we get. We have the constant mg over square root mg over k plus then this constant here, 1/2 square root m over kg. That's right here. And then with the ln function, then plus another constant c4. C4 is a constant. Now, so that's what we have for position. We need to determine the constant c4. So what is our initial condition? At t equals 0, x equals 0. Put these into our expression, and we get this. 0 equals m over 2k ln e to the 0 plus e to the negative 0 plus 2 plus c4. This becomes, this is 1 plus 1 plus 2, so we get m over 2k ln 4 plus c4 equals 0. So c4 equals negative m over 2k ln 4. So put our c4 into here, and we get our final result. Drum roll, please. X equals m over 2k ln e to the 2 square root kg over mt plus e to the negative 2 square root kg over m times t plus 2 minus m over 2k ln 4. This is a very complicated function. Let's see what it is near t equals 0 and what it is for large values of t to help us understand it more. Position near t equals 0. So let's do a Taylor expansion about t equals 0 of this function. Ft equals ln e to the gt plus e to the negative gt plus 2, where g is this. 2 times square root kg over m. This is the expression for the Taylor expansion. F at t is f at 0 plus t minus 0 f prime at 0 plus t minus 0 squared over 2 factorial f double prime at 0 to second order in t. Now, for our function here, f at 0 is ln 4, because this is 1 plus 1 plus 2 is 4. For f prime at 0, we get this. Now, I'm not going to work that out. I'll let the viewers, you viewers can work it out for yourself. F prime at 0 equals 0. And f double prime at 0 is 1/2 g squared. Isabel would like me to work out that thing in more detail. I'd like to do that, Isabel, but yes, Giselle. Giselle said it is very tedious. That's true, Isabel. It is kind of tedious, and this presentation is getting very long. Actually, this is the longest presentation we've ever done. I don't know how many viewers are still with us at this point. But I think if I go through this, it's going to be so tedious, and I'm going to lose even more viewers. So I'll tell you what. Let's do that. Okay, I'll tell you what. Why don't you try it on your own first? It's always good to try things on your own first to make sure you really understand it. And if you run into difficulties, let's get together and work it through together, okay? Okay, that's great. So I think we won't lose so many viewers if we do it this way. So f double prime of 0 is 1/2 g squared. Now let's put these things into our expression. So ln 4 is f0. 0 is f prime at 0. 1/2 g squared is f double prime at 0. Make those changes. This is what we get. ln 4 plus t minus 0 times 0 plus t minus 0 squared over 2 factorial times 1/2 g squared. So this term is just 0. For this term, let's square g. 2 kg over m. And then we get this. I'm sorry, g squared is 4 kg over m. So that 4 cancels out with the 2 times 2. And we get this, ln4 plus kg over m times t squared. Now, here's our expression for x. So this ln function in red is what we just expanded with our Taylor expansion. So let's put what we just found out. Near t equals 0 it is this. Now some things cancel out. This term, m over 2k ln 4, cancels out with this, m over 2k ln 4. So we are left with x equals 1/2 gt squared. Same as position when there is no drag force. When there's no drag force, acceleration is just g. And from the kinematic equation, we get x is 1/2 gt squared. This complicated function looks very simple when we make that expansion near t equals 0. Now let's look at what happens at large times. So here's our function. Now we want for large values of t. This term is e to the negative infinity, which is just 0. So this term we can cancel out. And then this term is very large, much larger than the 2. So the 2 we can just cancel out. And so this is what we have. When t goes to infinity, x is m over 2k ln e to the 2 square root kg over m times t minus m over 2k ln 4. Now, ln is the inverse of the exponential function. So this thing, once we work that out, it's just going to equal 2 square root kg over mt. And so this is what we get. M over 2k, these things here, plus 2 square root kg over mt minus m over 2k ln 4. Let's simplify this, and we finally get this. X equals square root mg over k times t minus m over 2k ln 4. So, at large times, the position is linear. So linear position means, take that derivative, you get a constant velocity, which is what we expect at large times. It's moving at the constant terminal velocity. And the coefficient of t is the terminal velocity. So the terminal velocity is square root mg over k. Let's look at the time constant for inertial drag. The time constant is this. We can write, this is our expression for acceleration. Now put in this, tau equals 1/2 square root m over kg into this expression. And we get this. 4g times e to the negative t over tau times 1 plus e to the negative t over tau squared. Velocity. This is the velocity. Now put in the time constant. This is what we get. Vt, that's terminal velocity, square root mg over k is terminal velocity, times 1 minus e to the negative t over tau, or 1 plus e to the negative t over tau. And now the position. This is our position function. Let's put in tau. This is what we get. M over 2k ln e to the t over tau, plus e to the negative t over tau, plus 2, minus m over 2k ln 4. The time constants for inertial and viscous drag are different. For inertial drag, when the time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. And the velocity does not always get closer to vt by a factor of 1 over e. But after a long time, such as 9 tau, they do get closer by the factor of 1 over e when the time increases by tau. Now, something very exciting is about to happen. Please pay close attention. This is so exciting. It's the most exciting part of the presentation. We are looking at the graphs for inertial drag. Here we are graphing acceleration on the vertical axis in terms of g, versus time on the horizontal axis in terms of tau, the time constant. This is what we get. When t equals 0, the acceleration was equal to g. It starts with a slope of 0, and it decreases as time increases. Initially, it is concave down. Then it becomes concave up, and it falls to 0. After a time of about 7 tau, it has reached steady state. Note that for viscous drag, it reached steady state after a time of 5 tau. Also, when t equals 0, a is g. When t is tau, a is 0.78 g. If it decreased by a factor of 1 over e in the time tau, it would be 0.37 g. At time of 2 tau, a is at 0.42 g. If it was decreasing at 1 over e each time the time increases by the time constant, it would be at 0.14 g. So when time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. But it does when we're at very high times, such as times greater than 9 tau. Now let's look at velocity for inertial drag. Here I plot velocity in terms of the terminal velocity vt on the vertical axis. We have time in terms of tau on the horizontal axis. Let's see what we get. Velocity starts at 0, and it increases. As it increases, the slope of the tangent to the curve decreases, meaning the acceleration is decreasing. Eventually, the slope becomes 0, and the velocity reaches the terminal velocity vt, and that happens at about a time of 7 tau, whereas it was at 5 tau for the viscous drag. When t equals 0, v equals 0. It is vt away from the final value of vt. When t equals tau, it is at 0.46 vt. If it was getting closer to the final value vt by a factor of 1 over e, it would be at 0.63 vt. When t equals 2 tau, it is at 0.76 vt. If it was getting closer to vt by the factor of 1 over e, each time we change the time by tau, it would be at 0.86 vt. So, when the time increases by tau, the velocity does not always get closer to vt by a factor of 1 over e. That only happens for large times greater than 9 tau. Now let's look at position versus time. Here is position on the vertical axis in terms of m over k. Time on the horizontal axis is in terms of tau. Here's what we get. Position is 0 at t equals 0. Initially, it is proportional to t squared. Then at the end, it is has a constant slope. When greater than 7 tau, it is a constant slope. Let's see how we can measure the drag coefficient for our falling coffee filters. The falling coffee filters had inertial drag. In that case, the drag force was kv squared. And we can write the inertial drag force as 1/2 CD rho AV squared, where CD is the drag coefficient, rho is the density of air, and A is a cross-sectional area of the coffee filter. From this, we can write K. K is 1/2 CD rho A. Terminal velocity. Vt is square root mg over k. So what we should do then is, this is our k, that's our k, so put it into here. And this is what we get. Square root mg over 1/2 CD rho A. Let's solve this for CD. Let's square it and solve for CD. This is what we get. CD equals 2mg over rho A VT squared. For the coffee filter, m was 0.00175 kilograms. VT, as we measured, was 1.51 meters per second. Density of air is 1.293 kilograms per meters cubed. And the radius of the cross-sectional area of the coffee filter was 0.075 meters. Okay, so let's put those numbers into this expression. 2 times the mass, 0.00175, times G, 9.8, over density of air, 1.293, times pi, times r squared. So pi r squared is the cross-sectional area, times 1.51, VT squared. And this is what we get, 0.66. Do you think this makes sense? Yes. Yes, Giselle, I think you are correct. It makes sense. Because for a sphere, CD was 0.5. And for a cylinder moving along its length, moving in the lengthwise direction, it was 0.8. And I think it's a good model of the coffee filter to be somewhere between the sphere and the cylinder moving lengthwise. So between 0.5 and 0.8, it makes sense. So I think 0.66 is a good answer. Okay, let's continue. Here's a summary of what we've learned today. First of all, we looked at drag force. There are 2 types of drag forces. One is viscous drag, where the force is proportional to velocity. Fd equals Vv. Then we had inertial drag, where the force is proportional to the velocity squared. Fd equals kv squared. The Reynolds number is the ratio of the inertial forces to the viscous forces. And from the Reynolds number, we can determine what type of drag force we have. We have inertial drag for high RE, greater than 1,000. And we have viscous drag for low RE, less than 1. Terminal velocity. When an object is dropped at rest in the fluid, the velocity increases, causing an increase in the drag force and a decrease in the acceleration. So we have the force of gravity down, the drag force up. The net force is Fg minus Fd. As velocity increases, Fd increases, causing the net force to decrease and the acceleration to decrease. Eventually, the drag force equals the force of gravity, and the acceleration is 0, because the net force is 0. And when that happens, the object moves at constant velocity, and that maximum constant velocity is called the terminal velocity, Vt. And here's our graph of velocity versus time for the coffee filter, and it reached a maximum final velocity of 1.51 meters per second. That's the terminal velocity. And from the terminal velocity, we were able to measure the drag coefficient of the coffee filter using this expression. And putting in the values, we got CD of 0.66 for the coffee filter. Differential equations. For an object dropped from rest in air, the differential equations for both types of drag forces were derived. For viscous drag, we got this. For inertial drag, we got this. The difference is this. We had a V here, we have a V squared here. And we solved those differential equations to obtain position, velocity, and acceleration as functions of time. The theoretical curves for position and velocity as functions of time matched the measured curves for a coffee filter falling in air. For both types of drag forces, the position is a quadratic function of time near t equals 0, and it becomes linear for large t. Time constant for viscous drag. For viscous drag, the time constant is tau equals m over b. And here's a plot of acceleration versus time. And we saw that when the time increases by tau, the acceleration gets closer to 0 by a factor of 1 over e. And we can assume that the system reaches steady state after a time of 5 tau, right here. Time constant for inertial drag. For inertial drag, the time constant is tau equals 1/2 square root m over kg. Here's our plot of acceleration for inertial drag. When the time increases by tau, the acceleration does not always get closer to 0 by a factor of 1 over e. That only happens for large times greater than 9 tau. We can assume that the system reaches steady state after a time of 7 tau, right here. Thank you very much for staying to the end of this very long presentation. Isabel, Giselle, and I really appreciate your viewing of our presentations, and we hope you come back again soon. Please be sure to like and subscribe. See you next time. Bye.